Okay, let's start the afternoon session of our second Astrobion. So the next speaker will be Dr. James Jenkins. Okay, he is PhD in astronomy by the University of Hertfordshire in UK. Okay, yeah. And he had his first postdoc in Penn State University, working on precision radial velocity spectrography. And later he moved to a fellow at Universidad de Chile for 5 years. And after that he got a fixed position there, okay? And now he's an assistant professor at Universidad de Chile, okay? He's author and co-author of more than 100 referred papers. He has a large experience on the study of exoplanets, especially on the search for Earth-like planets, okay? And he's also co-author of a Nature paper, recent Nature paper, about the discovery of Earth-like planet in the habitability zone of Proxima Centauri, the closest neighbor of our Sun. Okay, so let's enjoy the first class of Professor James Jenkins. Okay,
thank you, Marcel. And thank you to the organisers for inviting me here to Brazil. This is my first time in the country, first time in Rio, obviously, as well. And so, after this morning's two classes, I'm going to talk about something in a completely different regime. In particular, this morning, we were looking at system star formation, planet formation disks at really young epochs. Whereas now, so my area of expertise mainly is in radial velocity analysis. So the radial velocity search for extrasolar planets and the characterization of those planets. And so we have severe biases in our surveys, in the sense that magnetic activity, which we heard a lot about this morning, and which I'm going to talk about tomorrow, is a big problem for us in that it adds a lot of noise to our data. And so we bias our surveys to older stars, if we like, stars like the Sun, things that are kind of more along their evolutionary state. And so what I'm going to talk about over the next 4 classes, summarise here. And so today I want to look at how we probe the distribution of extrasolar planets. What tools do we use? How are we going to detect exo-Earths? That's the key question, at least for me. This is an astrobiology conference, and I'm mainly going to talk about... Hello? Let me put it in my pocket this time.
Yep.
Hello? Let me continue without. Okay. So, I'm going to talk about mainly today the kind of tools we use to discover exo-Earths. Because this is an astrobiology conference, as I said. The problem that we have as exoplanet hunters is that it's very difficult to detect exo-Earths. In particular, we really want to detect these planets around nearby stars, the nearest stars to the Sun. Hi? Okay. In the pocket this time. Okay. So we really want to detect signals or signatures of extrasolar planets, of exo-Earths in particular, orbiting the nearest stars. Those are the stars that in the near future we can follow up and look for those disequilibrium molecules, etc. Look for what really is an Earth-like planet, or look for exo-life if we want to extend it that far. Now, I don't want to sound pessimistic, because maybe I will over the next 3 classes, in the sense that I'm going to discuss the challenges that we face also. And the challenges are very difficult to overcome. Now, I focus on radial velocity analysis, in the sense that, I believe that radial velocity analysis will detect the first exo-Earths, and maybe, if we go back to my image there, Proxima b, in my opinion, is the best candidate we've got of what we class as an exo-Earth. It's so nearby, the star's small. It's an M dwarf. We heard this morning, M dwarfs constitute about 60 to 70% of the stellar population. And so the fact that it's only 4 light years away means that in the near future it's going to be one of the best candidate. We'll never find another planet closer than Proxima b. And so the fact that it's in the classical habitable zone means that it's going to be an excellent target to follow up for liquid water, if that's what we class as what an exoearth should be. But tomorrow, I want to look at what we've learned about the population. Because focusing observationally, of course, we're only reaching, and I'm going to hopefully convince you that we're only reaching the signals where we can detect Earths. For the 20 years that we've been studying extrasolar planets, for the 20 years, we've been focused mainly on the gas giant population. And we're going to go through some of the biases and the reasons for that. And of course, it makes sense that when we think about the techniques we use, that these are the easiest planets to detect. And so we'll discuss a bit about that. And then finally, on Thursday, I want to look at some real candidates. And particularly, I'll use Proxima b as a template, because we're reaching a stage now where there's a kind of convergence of technology, where we've got a convergence of the precision we can achieve through radial velocity analysis, the precision we can achieve with photometry, space-based and ground-based. And the key, or one of the real goals in the future, is can we directly image an exoearth? Directly image allows us to take spectra. It gives us a much easier route, if we like, to actually study the atmospheric constituents of the planet. And I want to convince you that that's not too far away as well. For the grad students and the undergrads here, I think in this field you're going to have a bright future if you're looking towards directly imaging exoearths, because it's not too far away, and particularly in Chile. I don't want to advertise the country I work in, but Chile's going to really push forward in this field when we get things like the EELT and the first and second generation instrumentation that will come along with that. Okay, so what I said here is that after this series of lectures, I want to give you a broad view of what we know in the exoplanet field, where it's going in particularly. So the topics for today are, like I said, I want to let you see what the tools are that we use. And I want to make my slides useful for each and every one of you, in the sense that I will have links on here. I'm going to explain quite a bit of detail how we extract these small signals, or how we're going to extract them. And so hopefully after this class it will be useful for particularly the younger people here looking forward in the field of how you can get involved. And so what methods are best suited, what biases do those methods have, and what exoplanet examples do we have. I say examples, I have a few examples just to show the differences between transit method, the radial velocity method, astrometric method, and direct imaging. Okay, so ISA showed a nicer version of this earlier, but I just wanted to highlight it again, in the sense that 2 minutes ago I just said we've been stuck searching for gas giants. I say stuck searching for them, those are the ones that we've been able to detect thus far. Big objects, generally close to their stars. And that's because of the bias that we have. So what we've really been doing is searching for other solar systems at the moment. Other solar systems in the sense that this outer part of the solar system. We can see here, particularly in mass and physical size, the solar system has a kind of step function. So we go from 1 Earth mass to about 15 Earth masses. The inner 4 small terrestrial planets, Rockies, and the outer 4 gas giants, taking away Pluto here. but the outer 4 big planets. So, one, there's already quite a bit of diversity in the solar system. And the question that we tried to answer a few years back, actually in about the mid-90s and beyond, was how rare or how common is our solar system? And of course, it's an interesting question to define. How do we define how common it is? In the sense that, are we just looking for a wide orbiting Jupiter? Do we need to look for these small planets, interior? Or, if we look at the scale, there's another question that arises that I'll talk about tomorrow, is where are the super-Earths? This seems to be a big population that we've found using transits and radio velocities. We have these population of planets that run from about a few Earth masses up to about 10 Earth masses. And that's kind of the canonical boundary between, let's say, rocky icy planet and a gas giant. That's where we're going to get kind of accretion. We're going to be unstable in the disk, and we're going to accrete gas at about 10 Earth masses. We transition from being rocky icy to gas giant. But in our solar system, we have none of these, and we'll see it's a big fraction. We also have no hot Jupiters either, of course. And hot Jupiters were the first planets that we detected because we were biased to them. And they make up about 1% of the population of planets, the hot Jupiter systems. And we have none of those in the solar system. So the real question statistically, and that's what one of the things we wanted to answer in the late 90s and still want to really answer the question, is how rare our solar system is. But I wanted to start with a very simple question. And a very simple question is, how do we define a planet? Because it turns out that it's not too simple to define. It was much more simple when we only had the solar system as our reference. Simple in the case that if we look at the IAU definition, which is kind of bandied around in the field, we need something that orbits a star, or the sun, if we think about the solar system. It needs to be large enough to maintain a spherical form under hydrostatic equilibrium, if we look at it that way. And then we introduced this third concept, that it has to have cleared out its orbit. And that was the death knell for Pluto. That came around because we started to detect these trans-Neptunian, or these kind of big bodies, and Plutinos, or dwarf planets, as they're now called. And so the solar system could end up having hundreds of planets. And so we rejected Pluto based on this ground. However, radio velocities started to show us, and then transits confirmed what we were finding, that exoplanetary systems are they're more diverse. They're much more diverse than what we believed originally when we just had one data point, which was the solar system. And so we added then that these planets should be not massive enough to ignite deuterium in their interior, and they have to be, the lower limit is similar to the solar system, so they have to be spherical. Now, the reality is at the moment, we haven't reached anywhere near that limit. And we're not down, we're just now getting to Earths. Kepler is getting to Earths, and I'm going to show you. The problem with Kepler is it's difficult to follow up the sample. It's brilliant statistically for the population, but it's difficult to do follow-up. And we're here in an astrobiology conference. We want to do follow-up. That's what we want to do. We want to look at the atmosphere. We want to look at the molecules, chase the chemistry. And it's difficult to do that with Kepler. And this boundary, this upper limit, we heard Fred mention about HR 8799, which I'll show the image soon enough. Are these planets, or are they brown dwarfs? And if we look at their thermal properties, if we look at their temperature, etc., they're brown dwarfs. However, certain evolutionary models, depending on what age you assume, if it's 100 megayears or so, will give you a planetary mass body. And further to that, also formation, so core accretion formation, and I'll talk about core accretion a bit more tomorrow, how we form these bodies. Core accretion can form planets, if we want to call them planets, up to about 40 or so Jupiter masses. So that's well into where we believe the brown dwarf regime is. And observationally, if we look at even the mass distribution, so if we want to say the mass function of exoplanets, also turns over at about 25 to 30, about 25 Jupiter masses. So in mass, if we look at the mass function, a physical characteristic that we can measure, then maybe the boundary exists at about 25 Jupiter masses. So what actually is a planet? The definition is fairly interesting, and it's worth maybe something we can discuss on Thursday. By the way, I want to say that I've left a lot of time in my slides for discussion at the end, or feel free to throw out thoughts and questions throughout the talk here. I welcome them. Okay, so let's get started. So what I want to do now is to show you the methods that we use. So this is the first class, kind of introductory class. I want to show the methods that we employ to eke out these signals. And I say eke out, we're going to see these things are very, very difficult to pull out the data. Even big gas giant planets, particularly in long orbits, if we look at radial velocity analysis, it's not an easy job to pull these out of the data, particularly because things like we don't get continuous observations from the ground. We're not in space. We don't get continuous measurements. And so we get interference from the window function. I mean, things that become really messy. It's difficult to pull out planetary signals. So the first thing I wanted to start on was actually something I've never employed myself. But it's important to highlight this method in the sense that it actually probes a different parameter space from what we do generally by radial velocities and by transits. So this has a completely different bias to those. And so gravitational microlensing, what we're looking at here basically is we have a source at far distance, generally in the galactic bulge. So there's many stars there. What we're really looking for is a system or a star passing between an observer and a far-off source, or a far-off star, if you like. And if that passing star between has a planet, what happens is there's some kind of the planet's gravity field, its potential acts like a lens, and what we get is an amplification, and I show that here, which is based on the Einstein radius. And we can calculate the Einstein radius directly from basically here we've got something that relates gravity, a constant here for a given solar mass, a given stellar mass, and then it's dependent on the angular distance at the source and the angular distance of the lens. And so what that means is what you really want is to get this alignment as close as possible in angular scales. You want that alignment as close as possible, and what that will give rise to is a bigger magnification, and I'll show the amplitude of magnification in the next slide. But just to put a number, typical Einstein radii are something like 1 milliarc second. That's what we're looking at in these scales. And so here's an example from Bellew in 2005, where what they found was a small Saturn mass planet on a wide orbit. That's what they detected. And I highlight here, I just want to highlight it's usually difficult to perform detailed follow-up studies. So now I did want to draw on the board. I wanted to set up a parameter space, particularly period against mass, but you won't be able to see it, I don't think, particularly at the back. So, but anyway, what I want to get across here is, what we see is we get a magnification of the star. So this is the star that's passing between the far-off stars and ourselves. And then we also get this little deviation, this excess magnification here, which is something like about 10% of the magnification of the star in this case. And that's large, considering this is only a Saturn mass planet. The problem, as I highlighted, is most of the time is very difficult to follow up these systems. But let's think about the biases here. So this is the first time I want to think about what this probes. And so what gravitational microlensing probes, it probes actually small planets in far-off orbits. Or at least it probes planets in far-off orbits. So it allows us, at the moment, to start looking at the distribution of small planets on wide orbits. And that's important if we look in period mass space, because it's very different from the biases that we'll discuss for the radial velocity method and the transit method as well. So, we talk about the first exoplanet being 51 Pegasi, B, and I'll show it. It's the first confirmed exoplanet. But it depends what we define as an exoplanet, of course, because the first planets outside the solar system were actually small Earth-like planets. I say Earth-like, but at least Earth mass. So only about 3 Earth masses. And those were discovered in 1992 by Alex Walsh and Steve Frail in their seminal paper. And they used something called pulsar timing, for those that don't know. So millisecond pulsars, and I wrote here, are pretty incredible precise atomic clocks. So if we have the methodology to measure those pulses with very, very highly sensitive instruments, and we're talking here, we get error bars in period on these things of like 9 seconds. So in time, we're looking at that type of uncertainty, only 9 seconds. And for someone coming from the radial velocity area, to have a period with an uncertainty of 9 seconds is incredible. And you'll see the difference that we've got in our measurements. It's much, much, much bigger. So what you do get from this is very precise measurements of the model that you incorporate. And in this case, it was a model of 2 Earth mass planets orbiting the pulsar. Now, we're in an astrobiology conference, so the question would be, how important are these 2 Earth mass planets if we are kind of looking at the future of searching for exo-life? Because these are, of course, pulsars, these are dead stars, if we look at it that way. What's the likelihood that these things have life on them? Very low. And just to let you see, here's the measurements that were made. We're covering about a year and a half of data for this pulsar. And you can see the double planet model that's employed. Now, I want you to remember this form, because I'm going to focus a lot on radial velocity analysis. As I said, that's what's going to be the key for the near future of finding the nearest exo-Earths. And we're going to see a lot of plots very similar to this. It's a dynamical method, very similar to this. It's a non-direct method, very similar to this. So you're going to see various morphologies over the next 4 classes of this kind of scheme. So astrometry, which is now going to be, it's important to discuss astrometry, because astrometry was touted as being one of the kind of future methods that we're going to detect small planets. It has a similar bias, almost similar bias, to the gravitational microlensing method, in the sense that it's biased to wide orbits, but it's biased to massive planets on wide orbits. So the astrometric method, what we're really looking at, that we can see here, if we look at right ascension declination, so on sky coordinates, astrometric method, we just want to basically measure the position of the star as a function of time. And if we look at this dotted curve here, this is the position of the star without any planets in the system. So we see, remember, these stars are moving through space, so they have proper motion. And they also have radial motion, of course, it's 3 dimensions, but in this case we have proper motion that sends it on this trajectory, this linear trajectory and right ascension declination. And then if we throw in a planet on a wide orbit, then we see deviations from that trajectory. Small perturbations given by basically this gravitational interaction between a wide orbiting planet and the star. And that allows us to essentially measure the mass of the and period of the planet. And here's how we can describe that where that perturbation, the angular perturbation theta, is proportional to the mass of the planet times the radius divided by its distance to the system. So what we want to maximise that angular perturbation. And we want to maximise it. It's maximised if both M and R are large, like I said, wide orbiting, big planets. And we minimise it by distance, so we want nearby. And you'll see in the final lecture, the final class that I'm going to talk about, we'll see that we have things like Gaia that's just flown and starting to produce data. In fact, the first catalogue was produced. And so astrometry may hold, at least for wide orbiting planets and big planets, is going to be excellent to study the wide orbiting population. And I want to say that if we look at exo-Earths, we need precisions that's going to reach easily 0.5 milliarc seconds. That's the type of astrometric precision we're looking at if we really want to look at the exo-Earth population. And this is an example, actually, of some real data. It was done using Hubble Fine Guidance sensors. This was already a detected planet by radio velocities, and it was also a small star, an M-dwarf star. So the perturbation of the astrometry is larger. But we can see that for star GJ876, that we can already detect planets through astrometry. But there's not many examples so far. It's very difficult, these measurements, given by basically the PSF of the stars. And so, I mentioned PSF, the point spread function. And that becomes important when we want to start looking at directly imaged planets. In the sense that, so I said that directly imaged planets are really where we want to go. That's where we want the field to be advancing towards. We want to be able to actually image these objects directly. We can take spectra, etc. We can actually map their orbits directly. Because everything else I'm going to talk about essentially is an indirect method. We detect them by just looking at the star and how the star varies. But direct imaging is that's what we want to do in the near future. And this is one of the problems with direct imaging, is that particularly from the ground, that's where we have the flexibility, we have the atmosphere to deal with. And this is the kind of difference that we can see. If we look at the point spread function of a star with and without something we call adaptive optics, and we'll go back through that. Adaptive optics is what we can use for those that don't know. It's a method that we can use to basically map the turbulence in the atmosphere. And we can correct for the turbulence various ways. We have systems like Shack-Hartman systems where we're basically trying to keep the light in the centre of the detector. And we use a closed loop system to do that, where we measure hopefully the star. The star's bright enough, we can use the star to look at the turbulence in the atmosphere, and we can correct the wavefront. That's what we're trying to do in this case. And when we do that, we can see the difference in energy here. So going from this little bulge to really a nicely well-defined PSF. And that's, of course, the energy we garner in this case is really high. And so when we do that, we can get some interesting results, very nice results. We're now reaching with the Sphere, for instance, on the VLT in Chile, or GPI on Gemini. We're getting to the point of where, I'll show some curves, but where we're reaching at least the young giant planet population. So, talking about biases and what we're looking at if we want to understand statistics, the direct imaging is biased to wide orbiting planets, but also we can add another dimension now. We can add age here, because it's also biased to young systems. Whereas I'm going to show radio velocities, transits, etc. are biased to the old stars, as I mentioned at the beginning. direct imaging is biased to the young population because we'll see later that tomorrow that if we look at evolutionary models, etc., these things are still hot. They're still hot, they're still luminous. They're much more luminous, in fact, very young. So that has another axis bias, and that direct imaging allows us to probe the young population of planets, and giant planets at that. Okay, so here's some examples. I said I wanted to provide some examples. And I work in radio velocities, which means I get data on plots. Direct imaging at least gives us some nice images to look at whilst we're here. And so here we've got things like Fomalhaut B, which has a nice disk as well that can be observed in scattered light. And we see 2 point sources separated by 2 years in time. And by that allows us to calculate an orbit for this object. Now this is, some people still believe that this is not actually a planet and it's contamination. We can discuss that in a few classes more. We'll see. But there's an array here. There's Kappa Andromedae, but look at these contrasts. We're going from 6 to 20 or so magnitudes, and here is the very first that was detected, 2-mass 1207b. And whether that's a brown dwarf binary is another, I mean, this we can discuss, whether that's a brown dwarf binary. But models predict it has something about 5 Jupiter masses or so.
James.
Yep.
Contamination, you mean background stars?
For this, actually, it is background. Yeah. There's a bit of literature on this to the point of, even though it moves, there was discussions of this being things like neutron stars and things like that. So it's unsure whether, at least to my knowledge at the moment, it's unsure whether this is really a bound system, whether that's bound to Fomalhaut. And I just put this in since it was mentioned earlier, HR 8799, because this is incredibly interesting in the fact that we've got a 4-planet system, or a 4 brown dwarf system, if we want to say. I'll call it a 4-planet system. It's dependent on the age in the models you use, what mass you can pull out for the planets. But we can see that we've got things on really wide orbits here, tends to getting on 100 AUs almost. And so, compared to our solar system, this is again something really exotic. Really massive young planets on super wide orbits. So where did they form in the outer disk, as was mentioned? Did they form through collapse of the disk? Which may, if we invoke formation models, maybe that does argue that these things are brown dwarfs. That they formed through fragmentation of the disk and they didn't form through the core accretion process or the oligarchic growth of small particles, of small dust. And so, as I said, this is really exotic compared to the solar system. So I really love this image, that's why I put it, to highlight the transit method, so I can say a few words about the transit method before we move into the details of the radial velocity technique. But this is the transit of Venus that happened a few years ago, and it really highlights well the transit method and the problems with the transit method, in the sense that we can see that this is not transiting right across the, let's say, the ecliptic point of the star, of the sun. And look at also around the sun here, there's something called limb darkening that we need to deal with. And for people that work in transits, limb darkening is a big problem for, number one, finding planets or transits in their data, but also for properly modelling the systems. And so here's what we get from the transit method. It's very, very simple in the fact that the deficit of flux, or the drop in flux that we see, is simply related to the radius of the planet squared over the radius of the star squared. It's very, very simple in that respect. And that gives us the bias straight away, one of them at least, is biased to to big planets, things with big radii. And it's also, of course, then inversely biased to the radius of the star. So big planets around small stars are easy to detect. We've got a bias there now, which is great. However, from what we know at the moment, we don't find many big giant planets orbiting M-dwarfs or orbiting small stars. And those should be the easiest to detect if there's many of them. Okay, M-dwarfs are fainter, so they're harder. I mean, they're harder to observe, but we can balance that out by the fact that there's many of them. They constitute most of the population of stars. However, we don't find many of these. There's only a few, what we would call hot Jupiters around M-dwarfs. There's only a few of them. And that has been thought of as being basically because the disks are smaller. So if we believe that there's a relationship between the star mass and the disk mass, then these are smaller disks. There's less material to form big planets in the smaller disk environment. And so that's the explanation for why we don't find many gas giants orbiting M-dwarfs. Because as I said, they should be easy to detect. If we look at a hot Jupiter system around a Sun-like star, we see a depth of a couple of percent in flux. About 1 to 2% generally. This was actually from the first detected transit planet in 2000, HT 209458b. And you can see that this, using data from Hubble, it's very, very easy to draw out and fit this data. Excellently, in fact. However, we've moved into the era of Kepler, and I said that, well, Kepler's been incredible for the statistics, for the population. He's done a great service to the community for the population of exoplanets. Harder in the fact that they're further away. They're fainter. The Kepler sample's fainter. These things mostly are further away, but we can see the type of diversity of transiting systems from Kepler. In the sense we get those big, deep, hot Jupiters, the ones with a 1, 2, 3% transit dips. But Kepler was also pulling out really small planets. And I'll show an example at the end here today of one of the most, let's say, Earth-like of the Kepler sample. But I just wanted to highlight that Kepler has really revealed, at least the short period so far, diversity of exoplanet systems. And it tends to be high. But looking at these biases again, the transit probability, so the probability of detection of a transit, is proportional to the radius of the planet over its semi-major axis. So this is an argument of size against distance. And that allows us to calculate probabilities. So use hot Jupiters as a standard in the sense that they're the easiest things to detect, because if we look at the radius distribution of basically substellar objects, or even stellar objects, going from the fully convective boundary of M-stars all the way down to planets, they've all got pretty much the same radius. Actually, M-stars, at least from models, tend to be a little smaller than Jupiter. But they've all got a pretty flat radius distribution. So hot Jupiters are a good benchmark for this. And as I said, if we look at the probability of detection of a hot Jupiter, so this is a Sun-like star, it has something like about 1% probability. In fact, things like 1 or 2% are excellent numbers for us in exoplanets to follow up for transits. A warm Jupiter has something like about 0.05%. Warm Jupiter being if we shift a hot Jupiter out to 1 AU, that's where it ends up having. We've got a drop there of a couple of orders of magnitude. Hot Earth's on the other case, so if we stick Earth at a couple of days, very close to a Sun-like star, we see something like about 0.1% transit probability. Now, if we then stick it out at 1 AU, where we really want to look at that population, then the transit probability again drops. It's now down to about 0.004%. It's very low. And so what we see is there's something like an order of magnitude difference between a Jupiter and an Earth. But then there's 2 orders of magnitude in difference if we shift from an orbit of a few days out to a 1 AU orbit. So we need to remember that we've got, and we'll see, we've got excellent facilities coming online, particularly in space. The likes of TESS, and I'll go through these facilities in the final class, looking at the near future that maybe some of you guys will be heavily involved in. But we need to remember that the probability is low, so we need to look at a big sample, particularly if we want to look nearby. Because of course, if we take the density of stars, then the real nearby objects, I'm going to keep making the case, they'll be found by radial velocities first, transit follow. And just to continue on from transits, there's also, we can utilise the transits if we can get multiple transits to look for deviations in the transit itself. So if we've got Kepler-like photometry, if we're really precise photometry, we can look for deviations in the modelled fit, particularly the centroid of that transit as a function of time, and try to probe particularly planets that are in resonances. So if we've got a nearby transiting planet first, such as this, if we look multiple times at that transit, we can look for deviations of the midpoint. And those deviations can betray the presence of another planet, particularly it's biased to resonances. It's biased to resonance planets. So things that have got an integer multiple of the period or so, where we get an exchange of energy between the two bodies and a perturbation of the orbit. And so we can search for transit timing variations, and the great thing about these at high precision, or the current precision we've got, they allow us to get down to the type of Earth mass regime. So at Kepler-like precision, we can be probing, and even less than Kepler, from the ground, we can be looking for Earth mass planets. But we're heavily biased, in particular, to resonance sites. And so if we've got a short period hot Jupiter, those resonance sites, we're biased to nearby resonance sites, in the sense that it's still really difficult to detect an exo-Earth. If we say it needs to be in the habitable zone, however we define that habitable zone, an AU. Okay, so we've looked at some of the methods we've used, mostly indirect methods and one direct method, the direct imaging method. And so now I want to look at the radial velocity method. This is what I've focused basically my career on so far. And this is what's now allowing us, at this moment in time, right now, to detect Earth mass planets, or approaching Earth mass planets, in the habitable zones of small stars. And that's one of the things I want you to take away as well, is the fact that at the moment, the biases that are inherent are meaning that we can only really detect them around small stars, around the M dwarfs. So things with 0.3, 0.4 solar masses and below. Now it's difficult because if we get down to the 0.1 solar mass regime, because the biases would allow us to find it much easier to detect exo-Earths around the lowest mass stars. The problem is spectrographs in general are not very efficient instruments. There's a lot of light loss. The throughput is quite low. In fact, the best spectrographs, things like Pharos, have throughput in the region of about 15%. So we lose a hell of a lot of light just breaking that light up to try and look at these stars spectrally. And things at lower mass that we're biased towards, they're too faint at the moment to get enough light into our instrument to actually be able to detect or have the high signal to noise that allows us to calculate these super precise radial velocities. So we can see, if we just apply Kepler's third law of planetary motion, and I wanted to show the image here just to highlight, I mean, this is real standing on the shoulder of giant stuff. In the sense, Kepler himself once said that why planets are on elliptical orbits basically almost drove him insane trying to understand that. So he spent a lot of time to come up with these 3 laws. And we can see that the radial velocity method is going to be heavily biased towards, very similar to transits, in the sense it will be biased towards big planets, big massive objects that are very nearby their star, because they're going to cause an acceleration of the star, an amplitude that's much higher, much larger, much easier to measure. And we use basically something called the Doppler effect that everybody in here has probably seen, where, and I'll show how we apply this in a second, where if we get an acceleration, we've got an acceleration of light, for at least of the star, we can calculate its change in frequency, basically applying the Doppler effect. Simply that the change in velocity over the speed of light times its source reference. And we can apply that by using some things called Echelle spectrographs. That's what we apply to really get high resolution and high wavelength coverage, and we'll talk about that later. And that allows us then to play this game. That allows us then to build these curves. So this is just time against velocity in meters per second. So just remember that. We're talking about meters per second, and I'm going to show what we can do for the time being with radial velocities. We're talking not just meters per second now, we're at the regime where we can start talking about centimeters per second of radial velocity precision. Man-made objects that can measure the velocity of stars light years away at centimetre per second precision. At the moment, we're below a metre per second. But this is what we're trying to build up. We're trying to build up, and of course this is just some simulated data, but we want to build up these radial velocity curves where we get 3 observables, particularly 2, the amplitude, or the semi-amplitude K, and the period, but we also get, of course, the shape, a couple of angular parameters, but we get the eccentricity of the orbit. And we can apply Kepler's law in this regime, where we can calculate the semi-major axis, or the distance, straight off, apply the velocity of the planet, and through momentum conservation we end up getting basically a mass. So we observe an amplitude, we observe a period, and we observe a shape. So this is a circular orbit, eccentricity 0, we can forget about the eccentricity and the longitude. And we get something here called the minimum mass. This is another bias, and a very important bias that has to be understood. I'm going to talk about mass over my lectures, but in reality what I'm talking about mostly is minimum mass. So when we said that we discovered Proxima b with 1.3 Earth masses in the habitable zone of Proxima Centauri, that was 1.3 Earth minimum masses. That's the smallest mass Proxima b can have. It could be slightly bigger, it could be a mini Neptune or so, but remember, we have inclination to worry about. We've got inclination of the orbit to worry about. So if these things are highly inclined, now the probability of them being highly inclined, of course, is very small. It's a cosine function, so it's small, but if they are, when we talk about individual systems, if that individual system's highly inclined, almost face on to our orbit, to our point of view, then its mass is significantly higher than what we measure from radial velocities. It's significantly higher than its minimum mass. And this just allows us to see how we apply in the radial velocity regime, how we can measure the amplitude from these curves. In the sense that this is the typical model we apply, where K, the amplitude, is just some constant divided by essentially the shape, the eccentricity, times the planet mass, minimum mass, remember, sin I is in there, against 1 over the square root of the star mass, times, again, 1 over the square root of the distance. And so when you run those numbers, you see that for an exo-Earth, this value, k, turns out to be about 9 centimeters per second. Sub 10 centimeters per second. So if we're limited at 1 meter per second, we're an order of magnitude away from the amplitude. Almost 2 orders of magnitude away from the precision needed for a statistical detection. So we need to be measuring stars at 2 to 3 centimeter per second radial velocity precision. So bear that in mind, that this is an incredibly difficult measurement to make down at big dynamical balls of gas, to measure them at centimeter per second precision. Okay, so how could we do that? And how do we do that? Well, one way to do it, the way we push through radial velocity measurements, is that we can look at basically a spectrum of the star. So we take our Echelle spectrographs, we take our instrumentation, we feed the starlight down through a fibre, an optical fibre, and the optical fibre illuminates our detector, or our spectrograph. It keeps the illumination stable. And that's very important. To illuminate your spectrograph, it has to be very stable. And we can do that. We can take a second fibre, and we can feed that second fibre by a thorium-argon gas lamp, or some other, it's called the simultaneous gas lamp method. Something that allows us to measure the intrinsic, or the uncertainty that we have from changes in temperature and pressure within the laboratory, the mechanical stability of our spectrograph. And so what we're doing essentially, we're measuring the velocity of the star, and then we're measuring a reference source in the laboratory, and we take the difference of the two. And that allows us to take out what we believe is the intrinsic noise, if we call it, of our measurements. And so the way we do that, we employ something called, so this is wavelength here against normalized flux. This is what a typical, this resolution, a typical stellar spectrum looks like if you zoom in on just a couple of atomic lines. Now, particularly the atomic lines here are iron. So it's a sun-like star, and they're blanketed in the optical by iron. So this is a couple of deep iron lines here. And we apply something called a binary mask. In red, I show what that looks like. It's simply, we mask out the continuum as much as possible, or any blends from other lines, and the centroids of this mask are where those lines are at rest in the laboratory, their rest wavelength. And we perform something called a cross-correlation analysis, where we cross-correlate all of these lines, a few thousand of them, against the binary mask. And by doing that cross-correlation and combining the results, we can then measure, basically we sum up the cross-correlation functions and get an incredibly precise measurement of the velocity of the star. And so there's a nice paper here by Pepe in 2002, you can go along and look at that, where it shows, it lays out basically the methodology for the simultaneous thorium-argon method. And if we want to look at that visually, this is visually what it looks like. I'm not going to show, I'll show a spectrum maybe like tomorrow, and we'll have a good look at spectral lines tomorrow. They're important here, but this is what a typical Echelle spectrogram looks like for the simultaneous thorium-argon method. We have this bright beam here along this dispersion axis. So this is the dispersed light of the star, and you can see these dark regions here that are deep atomic lines. And adjacent to that, we then have the thorium-argon lines, and you can see those are like blobs where we get strong thorium or argon lines that we can use to measure the intrinsic noise in our laboratory. And so we do that for each of those Echelle orders, as we call them, and we get these nice cross-correlation functions that look like nice Gaussians for each of those Echelle orders. And we combine those up And this is what we get. This is what our mean CCF, just as I showed the analytical form before, we just sum each of those CCFs up, those Gaussians, if you like, and then we can fit that with a really high precision, as I show in red. So I've got radial velocity in kilometres per second here on the X against the mean CCF, normalised mean CCF, and we can fit that by this red Gaussian function, and we can see we can get something down here, incredibly precise measurement, something at the level of 0.005 or so, 0.005%. So this is incredibly precise. That's what allows us to measure the metre per second at the metre per second level of the stars. That we have many orders, so we get many CCFs. We have many lines, and we can cross-correlate those many lines and combine those many orders to give us the high accuracy that we need, or the high precision that we need. And so then I said, when you do that, you're left over with basically the velocity of the star plus some intrinsic noise, some extra velocity from your instrument, from how you made the measurement in the laboratory. Now we try our best with technology to really minimise that, and I'll show HARPS at the end, where for HARPS we put the spectrograph in vacuum, we control the temperature and pressure at very, very high precision, but of course there's still some residual. HARPS itself, just to give you some numbers, HARPS itself is about, throughout the night, is about a metre per second stable, without doing any calibration. So, just observing with HARPS through the night, you can get 1 metre per second precision. Perfect. But we want better than that, and we've seen why. So what we do then is we look at the thorium-argon lines, and here we see them at HARPS resolution. HARPS resolution is about over 100,000 resolving power, about 115,000. And so what we're looking for is basically the shift again, delta x, delta lambda. And just by doing exactly the same technique, each of those orders, but now the adjacent order from thorium-argon lines, we cross-correlate in the same way, and we can pull out basically, again, very, very high precision thorium-argon radial velocity, or in this case, velocity. And so that's what we use for our drift correction. Now, this has been ongoing for many years in the way that it's not the only method, the simultaneous thorium-argon. There's also the iodine cell, or molecular iodine cell method, where instead of using a simultaneous thorium-argon lamp, where we have two beams, where we need basically two fibres that we feed, one by the star, one by the gas lamp, we instead take a cell of molecular iodine, most commonly, and we put that in front of the spectrograph, in the optical beam. So this is the Anglo-Australian telescope, this is the Anglo-Australian, part of the Anglo-Australian Planet Search, and this is their iodine cell. So it's a cell of molecular iodine that's controlled in temperature, and particularly it's controlled in temperature such that there's many lines of iodine in the optical. So you have your beam from the star, you pass it through your slit, you collimate your beam, you pass it through the iodine cell, and that gives you basically the stellar spectrum that we've seen, but also an iodine spectrum imprinted on the top of that stellar spectrum. And this is how we do it. We combine, as I said, the stellar light and the iodine light. So the stellar spectrum and the iodine spectrum, we pass the light right through the cell. And so what we have to do is forward model the observation. So we need to already know what the spectral profile of the iodine looks like. And so prior to that, what you want to do is use a Fourier transform spectrograph and look at the cell. So you take it to a laboratory, an FTS laboratory, you look at a resolving power of 1,000,000 or so, and that gives you something like this, where we can see in the optical, the iodine lines blanket the optical spectrum. That makes it an excellent wavelength fiducial to use. That gives us really high precision. But then we also need a template. So we need a template of the star. If we're going to forward model the combined spectrum of the star plus the iodine, we need a template spectrum of the star. And the way we can do that is we observe it at even higher resolution prior. So well over 100,000 resolution. Let's say this is your first observation. You observe it at really high resolution, and you bracket that with two rapidly rotating B stars, let's say. Things that don't have many lines. Have no lines in the optical would be the ideal case. And we can use that to then look at, with the iodine, how or let's say deconvolve the iodine from the template. So we create a template. This is supposed to be a point spread function free spectrum of the star. You need to do this for every star. So this takes extra time to do this. You also lose light. So you have an extra component. You're putting a gas cell in the beam that's going to eat up 20 to 30% or so of your light. So it's a little less efficient than the thorium-argon method, where you don't need anything in the beam. You don't eat up light. You don't lose some light. But you can model that, and we can see you get a quite really incredible wavelength solution. Super, super precise. And so what you then do is you can break it into small chunks of the spectrum. So you have this massive wavelength range at really high resolution, and you break it down into chunks of just a couple of angstroms, 2, 3, 4 angstroms maximum. Because that's where the PSF, the point spread function, varies across that kind of scale. So you break it down into many, many chunks, calculate your solution, calculate your Doppler shift for each chunk, and then you combine each of those chunks. And that allows you to reach about a metre per second also on the most precise spectrographs. Particularly on Magellan, there's the planet finding spectrograph, PFS, and that reaches similar to HARPS so far, about a metre per second. But the thing is, to be as efficient as HARPS, it needs to be on a much bigger telescope, because you're going to lose about 20-30% of your light to the cell. And so for historical reasons, I wanted to show the first confirmed exoplanet. Now it turns out, actually, I need to say the first confirmed because there was an exoplanet discovered by the radio velocity method in 1988 by Campbell et al., Bruce Campbell's group, that turned out in 2002, 2003 to be confirmed as planetary mass, so minimum mass. So it's about 10 or so Jupiter masses. But the first to be confirmed was back in 1995. So just to give this field has exploded in the past 20 years. So it's been 21 years or so since, just over 20 years since we first confirmed the first exoplanet, the first planet orbiting a sun-like star. And this is what it looks like. So I like to show this because this is a phase-folded curve. So now we're not looking in time. We're phased on the orbital period of the planet, which turns out to be about 4.2 days or so. And this was a hot Jupiter. You can see it has about something like half a Jupiter mass or so. So this is a hot Jupiter system. But I want you to look at the sampling. It's almost continuously sampled. There's only a small break in the sampling. And that's really crucial for radio velocity analysis to really detect these small amplitude signals. It's really crucial to really heavily sample properly sample those orbits. And just to really highlight the bias that we've got, so if I did draw up that diagram that I was going to talk about, we've got things like, we've got the microlensing that goes wide and small generally. We've got astrometry that goes wide and big. We've got direct imaging that goes also wide and big and also young. And then radio velocities and transits are biased towards the big and nearby. So things not on very short orbits or short period orbits, but also big. And so what we can see here is, if we really want to detect, we're thinking about low amplitude signals, if we really want to detect exo-Earths by this method, number one, we need to get that precision down to a few centimetres per second, which is pretty difficult to do. We're getting there. But also we want many cycles to be captured. Of course we would want continuous sampling, but that's just not possible. We have a window function to deal with. We need to observe at night if we're doing it from the ground. We have no radio velocity spectrographs that we can use in space, so we need to do it from the ground. We have a window function. Of course, the stars are not up all night, neither. So that's the problem. We've got these extra issues to deal with. And the window function becomes really problematic, and we'll see it in a few seconds. But we want essentially large amplitude, which means getting those uncertainties down as small as possible, and we want many cycles. That's what's going to allow us to detect these planets. And so I want to go through how we're going to do that, how we're going to be able to detect exoearths. Using the types of methods that we've been using for the past 20 years to detect gas giants. But I want to show the key issue that the key way we've moved forward. What allowed us to get, for instance, Proxima b, and the other, I'm going to show some other examples. So, look at that. For 20 years, we've been using this excellent method. It's excellent, of course, the Lomskargel method, or if we're looking at transit, the box-least squares. But this was written up in this was from the 80s. We're now in 2016. We're using tools that were developed in the 80s to try and find exoearths. I mean, this is why we're moving forward, and I'm going to show why. But this has been incredibly successful. I'm not no way putting this down. It's still heavily used, and we still use it for validation. But we've moved forward beyond that. What this method does, if we look at this orbital period, so essentially we're trying to sample frequencies in a kind of Fourier-like analysis. That's what we're doing here. You're just looking for cosines and sine functions in the data, essentially. And when you get a matching sine or cosine function, you get a strong peak in power. That's what we get. And we can do things like bootstrap analyses or whatever to try and calculate the false alarm rates or the false alarm probabilities. And when we get something like a false alarm probability of about 0.1, 0.01 in that ballpark, that's statistically significant. We can publish on that. And this is what something like that looks like. It will show 1%. This is much lower than 0.01% probability. I want you to put the benefits, so when you read these slides, you've got benefits and shortcomings. But of course, this is super fast. That's why it's still used. Current computer, it's milliseconds to run this on even large data sets. But it has problems. So if you use that method, let's say we've got two signals in the data. You use that method, you're doing something importantly wrong in the sense that what you're doing is you have to fit that one signal, and then you have to subtract that signal out and look in the residuals. So these things are not orthogonal. You're instantaneously destroying information from the second signal. So, okay, you're looking at one signal, that's fine, you found your one big signal, but it's very difficult then to find additional, particularly small signals, and particularly when there's a large ratio between the two amplitudes. So what we've been doing, we're moving beyond that to actually model the radio velocities in two forms, using maximum likelihoods and using Bayesian MCMC chains. And I'm going to show that because I'm going to leave you with some of the. This is the way, if anyone's interested to continue in this field, these are the methods that you want to look at for detecting exoearths by radio velocities. In the sense that what we can do with maximum likelihood periodograms, we can look at each of the frequencies, or each period, if you like, and we can calculate the likelihood for a given model. And whatever model you want to apply, we of course apply the Keplerian model shown before. But it's unlike the Lomskargel, where we have just cosines and sine functions. So what if it's got high eccentricity, above 0.6 eccentricity? Okay, the probability again is a bit lower, but it's not zero. We've got planets with almost 0.99 eccentricity. You're biased against those because you've assumed the signal's circular straight away. Whereas here, for instance, you can apply any model you want, including any eccentricity you want, but there's a key point, and I'm going to bring it up a few times in my talks, is that now we're at the stage where we can employ correlated noise models. So we're moving away from white noise models to correlations in the parameters, in the noise. But what you essentially do in this case is at each little period step, at each frequency, you calculate the likelihood, and you can calculate the likelihood against just a flat model. Just assume it's noise, the data. And then you can calculate the ratio. So it's delta log likelihood. And that ratio gives you probabilities straight away. So this is probabilities, essentially, straight away out of that. And you fit the data properly. And which means then you can also look for 2, 3, 4, 5, just by adding these signals in your data. Of course, the dimensionality increases. Every time you add a signal, you're adding 5 new parameters. Every time you add a new data set, then you have another 2 parameters that's being added. So you can quickly run away into 20, 25 dimensional space. But that's where we need to live with that, because that's reality. The other way we're looking at this is to employ Markov chains, MCMC chains, and Bayesian analyses, where essentially in this case we take our model again, and I'll just highlight. So we add excess parameters. We don't assume things in this case. We add, for instance, what we've got here is the gamma function. This is the offset, the actual real radial velocity of the star, plus an acceleration term if you've got maybe a binary, or you've got something on really wide orbit. We assume it could be a linear acceleration. You can, of course, you can put whatever you want in here, some parabolic function or whatever, or quadratic. But we have a long acceleration, a drift. Then we have the Keplerian model plus a white noise model. And I've left this as plus. Like I say, you can put it whatever you want, and tomorrow particularly I'll make the case for including red noise correlations in your model. And what you can do then is you can look in some period space. So we've just got n data points. This is walkers. You take a walker and you just look, assess the probability space, and let it walk away, given your model. And of course we do that with many starting points and find whatever we can find. And you can generate, after the burn-in period, you can generate some probabilities of the posterior. So we're maximising the posterior in this case. And that allows us very high precision. And it's very, I would say, it's probably one of the best way we have to detect signals. And you'll see that we detect lots of small signals. To give you to go a bit further, I wanted to tell you how we can do that, because the period space of, and we've seen it in the Lomscargo periodogram, for instance, the period space of radial velocity data is highly multimodal. You've got signals in there, you've got interference from the window function, from your sampling, your cadence, etc. So it's highly multimodal. And so we need to use other techniques, for instance, particularly tempering the chain, where we're maximising the posterior. So we start the chain somewhere, we're maximising the posterior, and for a lot of these systems it will quickly drive itself straight to the maximum of the posterior. Where the posterior in this case is just the likelihood times the prior that we assume. And so the problem is that it's not good for allowing you to sample the rest of the posterior space. You can't be it's hard to be fully sure that you've reached the maximum of the posterior. So what we can do is temper the chain. We can raise the posterior to some value, some parameter. And so what we're doing is kind of damping each of the peaks in the posterior. We're damping it. And what that means is it allows the chain to start wandering across the posterior space here. So instead of just diving straight to the maximum, which may actually turn out not to be the maximum, we allow the chain, by tempering it, to wander around, and if it is the maximum, we still see the maximum there. And then we can go to what we call a cold chain. So that's back to forgetting about the tempering, and that allows us to calculate the probabilities. But tempering is really key to wandering, or at least sampling the posterior and all the posterior. We can go further, and there's other DRAM, delayed rejection, things. We can talk about that later if you like. So for the final 10 minutes or so, I want to look at some of the detections we've made. I'm going to have to move a bit faster. So I'm going to show some examples that we've got of around sun-like stars. I'll show some around M dwarfs, and I have to talk about M dwarfs because that's, for the time being, that's where we're going to be finding our exo-Earths, or real nearby exo-Earths, in the really near future, or aka now. However, so what we've been detecting so far. Here's an example. This is using this Bayesian MCMC method, where here we've got a sun-like star, HD 41248, and what we find are two signals where we have a 10 Earth mass planet and an 8 Earth mass planet in this case. So you can see these are fairly circular orbits. They're very small amplitudes. I mean, look at what we're dealing with here. So we've got two data sets, both from HARPS, read some early data, an early data set and a late data set. And so what we can see here are these really, we're talking about, this is meters per second again, we're talking just a couple of meters per second amplitudes. And we can see this is about 100 and so up to 200, around 200 data points. Now this is what it takes to draw out these signals. There's just no way we detected these by Lom-Scargill analysis. We needed this tempered MCMC Bayesian analysis to really pull out these signals. We went further. I'll skip this for a second. More recently, just a couple of years ago, end of 2014, we published another pair of planets around Captain's star. So Captain's star is one of the nearest stars to the Sun, and it's high proper motion. It's a small M dwarf, and I need to highlight M dwarfs because it turns out they're quite rich in low mass planets. We see that from radio velocities and from Kepler data as well. Again, you can see we're at the region where we're pulling out 2 meters per second signals, and this was another pair of rocky planets around Captain's star. So now we're at the nearest stars to the Sun. We're detecting rocky planets, or at least low mass planets. Remember, it's minimum mass. One more example that I love to show is another one we found a bit earlier around GJ667c. So it's another M dwarf, another nearby M dwarf. And look at what we've got here, a system of potentially 7 planets. There's certainly 6 strong signals in the data. And I may come back to this in the final day because 3 of those, at least 2 of them, likely 3 of them, if this is real, this is almost flat. This is sub 1 meter per second. But 3 of these, and again, I'm showing phase against RV, each of these different data points, green and blue, these are different data sets. So not only are we just finding this, say, on HARPS data, which adds another level of uncertainty that there's something in the instrument, we're combining instruments, we're combining PFS, we're combining HARPS, and that's given us an extra level of confidence that these signals are real. And we can see GJ667c has at least 6 small planets, and 2 or 3 of them are in the habitable zone. So this is an excellent system to follow up for in the future when we want to really look at exo-Earth systems. And lastly, for the RV part, I want to show the complexity. And this is why I'm trying to really hammer home here that we need to move beyond Lom-Scargill analyses and stuff. But look at the complexity here. There's potentially 9. Our Bayesian analysis produces 9 planets in this system. There was 7 previously published by the Swiss group, a nice paper by Christoph Lovis, 2010. But then we went back, or one of my colleagues, Mikko Tuomi, went back just a couple of years later, took the data set, and finds 9 signals in that data set that do not agree with activity. And I'll show what I mean by do not agree with activity in the third lecture. But we can see, look at the complexity. This is in time. This is 9 signals that we need to model. Incredibly difficult. And the way we can do it, and just to pay homage to HARPS in Chile, is that we have this incredibly precise and stabilized spectrograph, the HARPS spectrograph on the 3.6 meter telescope in La Silla, in ISO. And this is, when I say it's stabilized, tries to be stabilized against earthquakes, which happen mechanically in Chile. And we actually can see earthquakes in our radio velocity data. You can see it in the thorium argon. It's quite interesting if you're a seismologist. This is the shell, and we can look more at those in the third lecture. But it's inside a vacuum tank. So it's fed by fibres. We have those fibres that are feeding the light. They're trying to stabilise the image on the spectrograph. But it's also placed inside this large vacuum. So it's pressure and temperature stable. Now, temperature is the first order stability that we need. Pressure is the second order stability because it changes the refractive index of the air, and we can see that in our radial velocities. So we really keep this really high level of stability. And that allows us to get 1 metre per second, sub 1 metre per second. Walking speed's 1.5 metre per second. So we're at levels much more precise than that. Walking along Copacabana Beach, we can do it at higher precision. So this is something to take away. Already sub 1 metre per second radial velocity precision. It's pretty incredible. I'm going to skip over Proxima B because I'll talk about it again. I'm going to use it as a template on Friday. I already showed some of the Kepler propaganda here that they like to show. Lovely light curves as diversity. And just to say that we'll talk about Kepler results tomorrow, and we'll hear another, my talk on the population. There'll be another one in the afternoon on Kepler exo, or at least the small signals from Kepler. But just to say, we've got over 200 planet candidates from Kepler at the time, so for statistical analyses it's excellent to study the diversity, to study the population. It's fantastic. But just again with that caveat that if we want to follow up. So I wanted to just show what Kepler has done. Kind of. At least one of them, Kepler 452b. And this wasn't me. This was also to highlight there's another J. Jenkins that works on exoplanets. John Jenkins from the US. So be careful when you look at names. And this is a lovely paper on Kepler 452b, and this was kind of touted as like an Earth 2.0. The star's very sun-like. Radius is just slightly smaller than the sun actually. But look at the transit depth that it requires. We highlighted this in the bias part. It's got a transit depth of 0.02%. That's incredible that we can pull out these small signals. And it orbits in the habitable zone. But I've got it there. It's only, we need to remember, we don't have radial velocities that actually detect the signal. We don't have the dynamics to detect the signal. So it only has about a 50% probability of actually being a rocket planet. That's the reality. And so, what we want to look at, as I've mentioned 2 or 3 times before, is the direct imaging. That's where the future's moving, to directly imaging the small planets. Where are we at the moment? Well, kind of the standard bearer on the VLT is Sphere on the VLT. It's our direct imager from ISO in Chile. And it's an extreme adaptive optics system. I mentioned the adaptive optics that's there to try and deal with the turbulence in the atmosphere and really get a PSF like it's been done in space. A kind of really a lot of energy in the PSF and a really sharp point spread function. And this can deliver strels of over 90% in the near IR. Strels being how close to a diffraction limited point spread function the actual measured point spread function is. And this is excellent for an 8-metre telescope, a large telescope. This is superb. And this little graphic here shows R-band magnitude against the approximate strels, where these purple dots are measurements. These are real measurements. And the purple here was the prediction in the H-band. And these are H-band measurements. So Sphere follows quite well operationally the theoretical predictions of the expected strel ratios. How good we could deal with the turbulence in the atmosphere, basically. How good we can reconstruct that point spread function. And they had a lovely paper out just a month ago or so. Wagner et al. 2016. I encourage you to go and have a read at that. Where they found this dynamically interesting system where you have basically this tight binary and a tertiary component, which is the brightest actually. So you've got a bright star and then a tight binary component, and around that bright star there's also a young giant planet. Remember young, again, this is the bias for this technique. and they were able to take some spectra and confirm, look at the temperature, 850 Kelvin of this object. So what we want to define it, let's just call it a directly imaged planet for now. But dynamically, this is a really interesting system, and this is the first detection coming out of SPHERE. So it's got a lot of legacy value.
What's the scale on that?
Sorry?
What's the scale on that?
Yeah, I'm not sure what this. I'm not actually sure what the scale is on this spatially. What is the scale? I did actually have it written down somewhere. In fact, let me come back to that. Yeah. Just to finish up, I wanted to show, as I said, this was about tools. I wanted to show that there's a kind of movement in the field that's happened observationally, and it's in the process of happening. There's the rise of these archive facilities, and this is, for me, this is fantastic. I love this in the sense that we're not too far away, or even there, the point of observers not ever needing to go observe, in the sense that a lot of that work I just showed through radio velocities, where we have all these big data sets, we didn't observe most of those data points. We took them from this archive facility. And so this is for me, this is a fantastic resource, that we now have these online repositories where we can extract highly precise data that's already reduced. It's already scientifically, it's already at the point where we can perform scientific observations and analysis. So it's a very cost-effective way for us to look for exo-Earths, in fact. So I encourage everyone to go to the Royal Astronomical Society website and check out the Astronomical Database Archive, because you can really get into this field without needing to be an observational astronomer. Just work on the analysis methods. And for the slides as well, I wanted to highlight some other packages. This is the second last slide. So the systemic package, for anyone that wants to really start studying radio velocities and transit work at the moment, take a look at the systemic package. It comes with published data as well, so you can get right down and start looking at systems fitting data. It's a lovely tool. There's a bunch of other tools. ExoNailer, that was done by one of the grad students at Catholica, where you can start fitting radio velocity data and transit light curves in an MCMC way. It's beautiful. EMC, our statistical package. So I just wanted to highlight a few of the websites, the resources that we've got that you can look at now if you really want to get moving in this field. So just to finish, and I'm right on time by the looks of it, we've seen some observational methods. We've seen how we can detect signals, radio velocity, transit, astrometry, etc. So I've shown how we go about finding planets. The next step is to really push the envelope and really dig out the smallest of those signals in radio velocity and transit, and that's what's going to open up the field for exo-Earth research, if that's where we're trying to look at. I've showed some software tools and highlighted some examples, and so I'll just leave it here saying that hopefully after the four classes that I give, hopefully you'll have a good understanding of the field in general, where it's going, and how you can become involved if that's what you really want to do, how you can get involved in this field of exoplanet detection, because in reality at the moment for astrobiology is a growing field, etc., but we need samples, and we're trying to provide the samples. Those samples are around the nearest stars, and so if you really want to get involved in this at the moment, hopefully after these classes you'll know exactly how to do that. So I'll leave it there and take any questions that anyone has.